Good day, dear colleagues. My name is Vitaly Slipchenko. I am a postgraduate researcher at Zaporizhia Polytechnic National University. Today I'll present our research called Classification of Helicopter Transmission Condition using Relative Spectral Features. This work studies vibration signals from helicopter transmission systems and proposes a method for detecting faults. Helicopter transmission systems operate under very high mechanical loads. If a fault appears in gears or bearings, it may cause serious problems and safety risks. For this reason, early fault detection is very important. One of the most common approaches is vibration analysis. By studying vibration signals, we can detect abnormal behavior of mechanical components. Helicopter transmissions operate under variable load conditions and high vibration levels. Because of this, monitoring systems are widely used to detect early signs of mechanical degradation. Early diagnostics allow maintenance to be scheduled before serious failures occur. However, traditional vibration analysis methods have some limitations. Many methods depend strongly on the sampling frequency of the signal. If the sampling frequency changes, the spectral characteristics may also change. In real monitoring system, measurement parameters are not always perfectly controlled. Therefore, diagnostic methods should ideally work independently of the sampling frequency. Another practical problem is that vibration datasets are often collected under different measurement conditions. As a result, signals may have different sampling frequencies or scaling parameters. This complicates the comparison of spectral characteristics. The goal of this research is to develop a reliable method for transmission condition classification. The proposed approach is based on relative spectral analysis of vibration signals. Instead of using absolute frequencies, we analyze the spectrum in a normalized relative form. This allows us to extract features that remain stable even when measurement parameters change. The proposed method consists of several main steps. First, vibration signals are recorded from the transmission system. Next, the vibration spectrum is calculated. After that, the spectrum is transformed into a relative spectral representation. Then informative spectral features are extracted. Finally, these features are used by a machine learning classifier to determine the transmission condition. In this approach, the vibration spectrum is normalized relative to the sampling frequency. This produces the relative spectrum. In this representation, frequencies are expressed in a normalized scale. As a result, the diagnostic analysis becomes independent of absolute sampling frequency. This improves the robustness of the diagnostic system. The idea of the relative spectrum is to represent frequency components as a fraction of the sampling frequency. This transformation makes spectral analysis independent of absolute frequency scale. Therefore, diagnostic features remain stable when measurement conditions change. At the next stage, features are extracted from the relative spectrum. Two indicators are used: spectral centroid and spectral kurtosis. The spectral centroid describes how vibration energy is distributed across frequencies. Spectral kurtosis reflects impulsive components in the vibration signal. As we can see in the plots, these features clearly distinguish normally and faulty conditions. The spectral centroid represents the center of mass of the spectrum. It shows where the main vibration energy is concentrated. Spectral kurtosis is sensitive to impulsive components, which often appear in the presence of faults. The dataset used in this research contains 1,158 vibration signals. Each signal corresponds to a specific operating condition of the transmission. Both normal and faulty states are included in the dataset. This allows us to train and evaluate a classification model. The extracted features are used as input to a machine learning classifier. Feature-based machine learning methods are efficient and computationally simple. They also provide good interoperability. The classifier learns to separate normal transmission operation from fault conditions. The experimental results show that the selected features provide good separation between classes. Both spectral centroid and spectral kurtosis demonstrate clear differences between normal and faulty states. This confirms that the relative spectral representation is informative for diagnostics. The classification results indicate that the proposed method can effectively detect transmission faults. These results demonstrate that the selected spectral features provide good class separability. The proposed representation improves the stability of the diagnostic indicators. This makes the method promising for practical vibration monitoring system. To conclude, a vibration-based diagnostic method for helicopter transmission systems has been presented. The proposed approach uses relative spectral analysis, which makes it independent of sampling frequency. Two spectral features were used for condition classification. The results show that the method can successfully distinguish normal and faulty transmission states. The proposed approach can be integrated into automated diagnostic system for helicopters transmissions. Future research will focus on expanding the dataset and testing additional machine learning models. Thank you very much for your attention. If you have any questions or comments, please feel free to contact me. My contact information is shown on the slide.